Hello and welcome to Lesson 20 on derivatives of exponential functions. Today we're going to be looking at how to find the derivative of these functions as well as applying the derivative to real life application. So I have included a little comic here for you, which won't necessarily make sense right away, but we'll come back to it. So to begin looking at exponential functions, we need to review our exponent laws for a bit. Starting with our product rule, which tells us that if you have two powers with the same base, when you multiply them, the new product is just the same base, and you find the sum of the two exponents. Now, the quotient rule similarly tells us if you have the same base and you're dividing them, we subtract those exponents, and we have to have that a to the power of n is not equal to 0, which would mean that a is not equal to 0. So we don't have a 0 divisor. Now, our power of a power rule tells us that if you have a to the power of m and this itself is to the power of n, that means you're multiplying a to the power of m n times. So then your new power is m times n. And finally, the logarithm rule tells us that for base a, if we have exponent log with the base a there as well, and m, then this is really just m. And similarly, if you have a to the power of m and you take the logarithm of this with a base of a, then this is just the exponent m. And so we will actually be using this property today, so please familiarize yourself with it if you have forgotten. Now, we are looking specifically at the exponential function and the logarithmic function. So our exponential function is y is equal to b to the power of x with our base b, and base b is positive and b is not equal to 1. Now we can choose any value of x, but we just don't have those negative bases. Now, logarithm function tells us a y is equal to log base of b of x, and this is the inverse of the exponential function. And just to give you a refresher, if we have an exponential function that behaves like this, then, and this is y equals bx, then our logarithmic function will look something like this. And we have the y equals x line, which is our how our inverse functions are reflected. Now, some key features of the exponential and logarithmic function, and now we're specifically looking at the natural log and the Euler's number e. So with these two, we do have for our exponential function, the domain is all values of x. But with all values of x, we do have that our output is y is greater than 0. So we cannot have an output that is less than 0 or even equal to 0. And that's what we see here. We see that we are approaching the y equals 0 line, but we don't actually reach it. It does also pass through the point 0, 1, which is part of the exponent properties. When you have anything to the power of 0, that is equal to 1. So same with here. If we have e to the power of 0, this is equal to 1. Next, we have that e to the power of the natural log of x is just equal to x. And again, we have that x is greater than 0. And our horizontal asymptote is y equals 0, again, as we see here. Now, for the natural log function, we have the domain as x in R, but now x is greater than 0. And as you can see, the domain and range here are the same because, again, it's inverse functions. And same with the domain and range here, they're just swapped now. So for a range now for the natural log, we could have all values of y in R given our restriction. It also does pass through the point 1, 0, and that's pretty much coming from here as well. When we think, okay, now we have an output of 1, so what was the exponent of Euler's number to give us that output 1? The exponent was 0. And the natural log of e to the power of x is x. Again, think of what is the exponent of e here, which is just x. And x can be all values, all real values here. And we have now a vertical asymptote, x is equal to 0. And so actually this one I should draw it a little bit better to have that point in there, our 1, 0 point, something like this. and we just have that vertical asymptote there. So we don't actually ever reach x is 0 with the natural log function. Now, what is the derivative of the Euler's number function? So if we have f of x is equal to e to the power of x, the derivative is actually just itself. It's e to the power of x. And just in case you need a reminder, Euler's number is the natural number, and it is approximately 2.718. So now knowing this information, I am going to go back here for a moment to our comic at the beginning. So here we have that the rational function gives a book to x squared reads the book, and it's like, whoa, and now it has become 2x. And now it gives a function to our natural exponential function, and it tells it, read this, it will change you. And reads it and says, meh, it was all right, I guess. And 2x is now thinking, how could anyone not be affected by this book? Because it was the derivative book, and we can clearly see that the derivative is the same, so we do actually have that the function does not change. And I hope that helps you actually remember that the derivative of the natural exponential function is itself. So now let's see a proof of why this happens using our first principle. So using the definition of first principle, we have that the derivative of f of x, so again, remember f of x here is e to the power of x, is defined as this limit with f of x plus h minus f of x over h. And now we just substitute those values here. So we have e to the power of x plus h, take away e to the power of x. But using exponent laws, this is just e to the power of x times e to the power of h. And so I can actually factor e to the power of x. And because my limit has to do with h and not actually x, I can see this as a constant. And then I can factor this out so that I have e to the power of x here, and then my limit is actually e to the power of h minus 1 over h. And so this limit is actually a special limit, and it is going to give us a value of 1. The reason for that is this limit, this part, is actually equal to f prime at 0. So this would just be e to the power of h plus 0, and the 1 is just e to the power of 0. And then we just have in the denominator h plus 0. And we see that when simplified, these two limits are the same. So then we have that f prime of x is equal to e to the power of x, which was what we factored out there, times f prime of at 0. And this is a property of Euler's number, and we know that f prime of 0 is equal to 1. So f prime of x is actually equal to e to the power of x times 1, which is just e to the power of x. Now, let's try a few examples. So starting with our function e to the power of 4x, and we want to find the derivative. And I hope you can see right away that this is a composite function with e to the power of x, but now our inner function is 4x. So I define my outer function as g of x, which is e to the power of x, and my inner function is h of x is equal to 4x. So then f of x is actually g of h of x. And here I'm just using chain rule to find to the power of 4x by d4x, and then d4x by dx. And the first part, we're just using the definition of the derivative of the natural exponential function, which is just itself, and especially with respect to 4x. And then d4x by dx is just 4. So then we have 4 times e to the power of 4x. And so really, we just leave that exponential function, and we just found the derivative of that exponent, which is 4. So if you have a composite function involving e to the power of x, and specifically if it's of the form f of x is equal to e to the power of g of x, so your inner function is the exponent, then the derivative of the function, the original function, is the function itself, So this is just f of x times the derivative of the exponent, which is g prime of x. And in Leibniz notation, we have what we saw above here. So this would just be f of x, and this would be g prime of x. Okay, now let's try some examples here. So given g of x is equal to e to the power of x squared minus x, we apply the chain rule. And so we first find the derivative of the main function with respect to the exponent, so x squared minus x, and then the derivative of the exponent with respect to x. So the first part, we just have the function itself, and then the derivative of the exponent will be 2x minus 1, which is what we see here. And I'm just using my derivative rules a little more freely now, because at this point we're comfortable using them and we're applying them to more complex functions, so you can just state them and it's assumed that you know which one you're using. Now, again, we have another function, h of x is equal to 4x cubed e to the power of x. And now we are actually applying here the product rule. Because you can see that e of x is not a composite function. It's just the exponential function. And here we have another function times the natural exponential function. So then we have the product rule. And so the first term is just 4x cubed. And this is the derivative of e of x. And then we find the derivative of 4x cubed times e of x. And if you expand this or find these and expand, we have 4x cubed e to the power of x because that derivative just stays the same. And then here we have 12x squared times e to the power of x. And I would suggest do a little bit of tidying up here and factor out anything just to have a nicer looking expression. So I see that both of them have that 4x squared and e to the power of x in common, so I factored that out, and then I'm left with x plus 3. Now, I would suggest you try these four on your own, and if you're ever unsure, especially with differentiating problems, you can always search up derivative calculators and check your answers for any of these, or leave a comment on our Google Classroom to check your answer. Now we can also apply equation of the line of a tangent with exponential functions. So given the function y equals e to the power of x over x squared, we want to find the tangent line at x is equal to 2. So what I'm going to do first is rearrange this. So x squared is going to become x to the power of negative 2. So then I'm going to apply the product rule. So again, I mentioned before, I sometimes use the product rule instead of quotient rule, but you can also use quotient rule here and check that you get the same answer. So now, finding the derivative here, we are applying the product rule. So first term e to the power of x, and then the derivative of x to the power of negative 2. And then in my second term, I have the derivative of e to the power of x, and we just leave x to the power of negative 2. And in my first derivative, I have negative 2, which is the exponent, and then x to the power of negative 3 now. We subtract 1. And over here, we just have e to the power of x, and then x to the power of negative 2 just stays as is. And now again, I'm going to do a little bit of tidying up. I'm going to rewrite this. So my negative exponents are now in my denominator. So I have x cubed here and x squared here. And I'm going to find a common denominator of x cubed by multiplying this term by x. So then I am left with negative 2 e to the power of x plus x times e to the power of x. And now I want to find that slope at x is equal to 2. So I can just leave this here as is and substitute now x is equal to 2. So doing so, I will have, and I actually did factor it here just for simplification. So I factored that e to the power of x out, and I was left with negative 2 plus x. So then in this bracket here, I can see that I have a 0. So I don't even need to look at these terms because I have a 0 here. So then we have the slope is equal to 0, and then we have the tangent is horizontal. And if we graph this here, and you would also have to find the point. So we have y at x is equal to 2 would give you e to the power 2 over 4. So then our point is 2 e squared over 4. And because this is a horizontal line, so m is equal to 0, then the equation of our tangent is going to be mx, which is just 0, plus b, but in this case, it'll be e squared over 4. And now, looking at our graph here, in red, we see the original function, so e to the power of x over x squared, and we can now see that that the equation of the tangent, which is y equals e squared over 4, which is approximately 1.84726, is exactly this blue line that we see here. And we do see that it does cross the, or it does intersect with the graph at precisely that point at x is equal to 2. And it is also a horizontal tangent. Now we're going to also combine trigonometric and exponential functions. So we've seen both now, so let's put those two ideas together. So given the function e to the power of sine of x times cosine of x, we want to find the derivative here. And I want you to consider first what derivative rules we're going to apply here. Because first we have a product, but then we also have a composite function. So already based on that, I know that I'm going to have one chain rule and one product rule in there. So here we have the steps to find the derivative, and I want you to, as we go through this, try to identify which derivative rule is being applied here. So in the first line, I just taken the derivative of the exponential term times cosine of x plus the exponential term times the derivative of the trigonometric function. And I hope you see that this is the product rule. And now, to find this derivative itself, this is actually my composite function. And now is where I have the chain rule. So here we just have e to the power of sine of x, and then we just find the derivative of that exponent, which is sine of x. And the cosine of x just stays. And in the second part, we have negative sine of x, which is the derivative of cosine of x. And this is just our trigonometric properties, or the derivative of the trigonometric functions that we saw in our previous lesson. And now we have e to the power of sine of x times cosine of x twice, because this is now the same derivative. Or the same derivative property. So I guess we do add that here. So I'll just write trig derivative. And so here we also have the trig derivative. Because we know that the derivative of sine of x is cosine of x. And here I've just distributed that negative here. And now I can see that I have e to the power sine of x in both of these terms, so I can factor that out. And then I'm left with a bracket of cosine squared of x minus sine of x. And it would be fine to leave this just as is, and then that is our derivative. We can now also find second derivative for exponential functions. So we've seen higher order derivatives, and now it's the same process. You just find the first derivative and then find the derivative of that to find the second derivative. So given the function y equals negative 3 e to the power of x plus 5, we want to find the second derivative. So using our derivative rules, we know that this will be our resultant derivative. The reason for that is e to the power of x, or let me write it here for us, is going to be just, we can factor out that negative 3 because it's a constant. we have this. And we know that this derivative itself is just equal to e to the power of x. And we also know that d5 by dx, because it's a constant, is just 0. So then we're just left with that negative 3 e to the power of x term. Now differentiating this again, we get the same result. And again, this comes from here because we're finding that same derivative. So negative 3 is factored out because it's a constant, so our constant multiple derivative rule. And then d of e to the power of x over dx is just e to the power of x. And so we now see that for this function, f of x is actually equal to f double prime of x. So the first and second derivative are the same. This doesn't always happen, especially if you have other terms that are being added here. So if you have, for example, plus 2x or x squared there, I hope you can see that your derivatives will be different. And now here, I want you to try finding the second derivative for this function. So here you can double check that you would have gotten the following second derivative. And so we have one term that has the x, and then we have one that is just 4 times e to the power of 2x. And again, this comes from the property of the derivative of the exponential function. So please try it on your own and confirm that that's what you get. And now I want you to think, how can we generalize what we've seen so far with the derivatives of the natural exponential functions to all exponential functions that are of the form y equals b to the power of x? And b now does not necessarily have to be e. It can just be any number. So the derivative of that function is actually going to be b of x. So we do have that same property, so b to the power of x. Oh, and I should have a prime here. And then we have a product here, which we are multiplying now by the natural log of b. And so why this happens, and you don't need to know this for the sake of this course, but I am going to show you a little bit of why that happens. It starts with this property of the natural log, which is when we have e to the power of the natural log of x, this is just equal to x. So now, if I'm finding the derivative of b to the power of x, I can actually rewrite this as e to the power of x times the natural log of b. And again, this itself comes from the property of the natural logs, which tells me that if we have b to the power of x, and you take the natural log of this, then we can actually take x and multiply it, and then have the natural log of just b. And so from here, I can do a change of variable. So I would let u be equal, and actually going back to here, because we want to work with this limit. So I would let this be equal to e to the power of h natural log of b. So then if I let u be equal to h, the natural log of b, and I can rewrite this as h to the power of, oh, sorry, u over. Okay. And as we have h approaches 0, then we can also see that u is approaching 0. So our limit doesn't change there. But now in our limit, we can write, and we have, so we have now this new limit, which is just your variable u. So I've just substituted u over here for our exponent. And then in my denominator, I had h, which now I rewrote this as this fraction over here. And now I can actually rewrite this. So I have natural log of b. And this is a constant for our limit because it does not depend on u. So then my limit is just 0 of e to the power of u minus 1 over u. But if you remember, this is that same of f prime of 0, which was 1. And so we can actually write this as just natural log of b. And then we would have that over here. And we are showing that we did show first this part, and then just applying the first principle. So if we're using first principle for this function here, then you would be able to find this original limit in there somewhere, and then you will find now that this equals to the natural log of b. And then you would also be left with just an e to the power of x, or sorry, b to the power of x there as well. And that would be your constant because it's not dependent on h. So then factoring that out, you would have this derivative over here. Now let's try an example. So we have the function f of x is equal to 5 to the power of x. And we also have a composite function. So g of x is 5 to the power of 3x minus 2. And we're going to now use this definition to find the derivative of both of these. So with our first function, this is just the definition. So f prime of x is going to give us natural log of 5 and just the function itself, so 5 to the power of x. And that's pretty much it. Now for g of x, we have to apply the chain rule. So we will define h of x to be 3x minus 2, which is that exponent expression there. And then g of x is actually 5 to the power of h of x. And using the definition of the derivative of the exponential functions, we have that g of x is equal to the natural log of 5 times 5 to the power of h of x, and actually times h prime of x. And here we had found that h prime of x, so the derivative of the exponent, is based on 3x minus 2. It's just equal to 3. So that's that 3 over there. And then just rewriting this to have it look a little bit nicer, we have 3 times 5 to the power of 3x minus 2, and then that natural log of 5 there. Now we can generalize this. So if we have a composite function with a base b and an exponent of g of x, then given the function f of x, which is defined as such, the derivative of f of x is equal to the natural log of b and b to the power of gx. And this is, again, just the derivative of an exponential function and the derivative of its exponents function, so g prime of x here. And that's exactly what we saw here. Now, one last example here, we have a application question. So the number n of bacteria in a culture at a time t in hours is represented by the function n of t, which is equal to 1,000 times 30 plus e to the power of negative t over 30. And first we're asked, what is the initial number of bacteria in the culture? And the initial time, or the initial number occurs at t is equal to 0, which is our initial time. So all we're doing here is just substituting t is equal to 0 and finding n of 0. So if t is 0, then that whole exponent there is just 0. And so this part is just 1. E to the power of 0 is 1. And then I'm left with 1,000 times 30 plus 1, which is 31,000. Now, our next part asks us to determine the rate of change in the number of bacteria at time t. So rate of change, remember, is our derivative. So given the time t, so a generalized time, we're finding our derivative function, so n prime of t. And this is going to be equal to 1,000, and inside the bracket, so 1,000 is just our constant multiple rule, so that's why I left it there. And then we want to find this, the derivative of the bracket. So 30 is a constant, so the derivative is just 0. And because I have some rule here, then this is just 0, and we find the derivative of e to the power of negative t over 30, which is our composite function of an exponential function. And based on what we just saw, this one is just our natural exponential function, so we don't have natural log of e. And so then I'm left with negative 1 over 30, which is the derivative of the exponent, and just the function itself, which is e to the power of negative t over 30. And then here I've just simplified this with that 30 and the 1,000. And this is my derivative function. Now we're asked how fast is the number of bacteria changing when t is equal to 20? So we want to know the rate of change at time is equal to 20. But we already have our derivative function, so then I can just substitute the value of 20 there. So n prime at x is equal, or t is equal to 20. And I will find this expression here, which is approximately negative 17.1, which means that the bacteria is actually the rate of change is negative. So the number of bacteria is decreasing at a rate of 17.1 per hour because our time was an hour. And finally, we're asked to determine the largest number of bacteria in the culture during the interval t is between 0 and 50 inclusive. And I hope you remember this is now our extreme value algorithm. So we want to find the local extrema on this interval. So we know that, and we're first analyzing just the domain of the function. So we do have that e to the power of x is greater than 0 for all x. So then this value, our derivative function, is dependent on just the negative 100 over 3 because this is greater than 0. So then it's actually just going to be less than 0 for all values of t. So that means the rate of change is always decreasing, and we'd expect the maximum to occur at t equal to 0. And so here, I would just suggest you check this for yourself. So just check the endpoints just to make sure. And you should find that n at time 0 is equal to 31,000. And then n at time 50, our other endpoint, will be 30,188. And we can clearly see that this is the bigger value so that our maximum is occurring at t is equal to 0, which is what we were expecting anyways based on just our derivative function and analyzing the derivative function. So sometimes you'll see that you don't have to actually apply that whole complete algorithm just because of how your derivative function is defined. And so a question just to end this off, what is happening to the number of bacteria in the culture as time passes? So as time is approaching infinity, so time is passing, then e to the power of negative t over 30 is actually approaching 0 because this is getting more and more negative. So then we know based on the function that we have for e to the power of x, we have something like this, but now because we have that negative, we have it flipped, so it'll be something like this. So as t is approaching infinity, then this value is approaching 0. So then going back to our original function, we are only caring about this portion, which is 1,000 times 30. Oh, I have way too many zeros there. Okay, slight error, I'll fix this for you, but this should be 30 there. And then, there we go, that's much better. We have 1,000 times 30, so it'll be 30,000. So then the number of bacteria is decreasing and approaches 30,000 over time. Okay? And now we also saw an application of the exponential function, and that's the end of our lesson for today. So you have some practice problems here, and as always, check Google Classroom for any additional tasks, and don't hesitate to reach out if you have any questions, and I'll see you all next class.